Hi, welcome back to this video series on cryptography. In this segment, we will continue looking into the counter mode. We looked at how to make use of the padding oracle and recover the plaintext length in the previous segment. In this segment, we will make use of the padding oracle and learn the secret message itself. We will disclose the plaintext by just using the padding oracle. The padding oracle accepts modified ciphertext and will give feedback whether the resulting plaintext is well formed or not from a padding perspective. If something is wrong during padding calculation, we will get an error message. The attacker can make use of that error message to recover the complete plaintext. To make things easier, I'm going to make some assumptions about the number of blocks. Okay, I will assume there is only one block. Okay, which makes it slightly easier to explain than having multiple blocks. So I'm assuming that you have already watched the previous segment that we talked about the counter mode, how it works, and what kind of padding is performed. So please watch those videos if you have not watched them first. Okay, so the goal of this segment is to show to you that we can decrypt the plain text if there is a padding oracle, and the counter mode is used with padding enabled. Okay, not all libraries support padding with counter mode, some do, but what happens if padding errors are leaked? Okay, that's what I wanted to show to you. So let's assume there is only one block. Okay, so the message itself is made of only one block. Say, I'm just going to make it simple. Let's say the message is made of only 5 characters, right? That means the remaining 11 bytes are, I'm going to make only 5 characters of message just to start with. 3, 4, 5. Okay, this is our message, the original message. So what it means is that the remaining 11 bytes, I'm working with AES, which is 16 bytes block cipher. Therefore, the remaining 11 bytes are padded. Okay, so 11 bytes of padding. What we mean by padding is that we will be adding 11 bytes. In hex it is B, right? P, B, B, and so on. 11 times we do. Okay, and so on 11 times. So totally 16 bytes. That's basically the idea of padding. And now we have 11. This is, assume this is 11 B's, right? 11. And here is 5 bytes. So totally 16 bytes. All right. So now we learned earlier how to take a ciphertext and learn the message of the plaintext. Okay, using padding oracle. So we can compute the length of the plaintext just using the padding oracle. So that's not a big problem. So now the challenge is, can we find what is there? What is the message? Can we find out these messages? How do we find that? So here comes the nice idea. So the idea is basically adapted from the padding oracle attack that was developed for CBC mode in particular. So I'm going to sort of tailor that attack to the counter mode. Okay, so the step one is, what if I change all of these bytes to say instead of 11 I make it 12. C, C, C. Okay, in hex C means 12, right? Now the padding oracle will say your resulting plaintext is wrong, right? Because you don't have a C here necessarily. Okay, so by the way, we don't have the message. We have to do this in the ciphertext. So let me be more clear then, so that you're not confused. Okay, so this is how internally it will be when you decrypt a 5-byte message, right? But attacker doesn't have the internal structure. They only have the ciphertext. So what they're going to do is they're going to start modifying the ciphertext in such a way that when the decryption oracle decrypts the ciphertext, they're going to have, instead of BBB, they're going to have CCC. And now padding oracle will fail because we didn't have a C here. So that means the attacker now can start trying by 1 byte at a time until he gets the complete padding successful. Okay, that's basically the idea I'm going to talk about in a little more detail now. So let's consider now the scenario with the ciphertext. We have the ciphertext that we would like to manipulate. So let's assume we found out that only the first 5 bytes of the ciphertext actually correspond to the actual message that we discovered using the padding oracle. Okay, so 1, 2, 3, 4, 5. This is the ciphertext. Now I'm talking about a ciphertext. The remaining 11 bytes, remember 11 bytes, those are padding bytes. From here onwards, I have 11 bytes. Let's assume I have 11 bytes. These 11 bytes are padding bytes. Okay, padding bytes. So what I'm going to do is, since I know these 11 bytes will be decrypted into B. I don't know the key, but I do know for sure these bytes will be decrypted into B, 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 B. Otherwise, padding would have failed right at the very beginning. So we will have 11 Bs. We know for sure. Okay. So question now is, what can I do so that the resulting ciphertext can be modified in such a way that when the decryption oracle decrypts our ciphertext, it gets CCC instead of BBB. So what we can do is very simple now. Let's say we take one of the bytes here. Let's call this C for a moment. Okay, we take that byte C. We XOR that byte with what are we going to XOR against? We're going to XOR it with a B. Okay, that the byte number here, B means number 11, right? In decimal. So we take the byte, we XOR it with B. Why are we doing that? Okay, remember how the counter mode works. It takes the ciphertext, it's going to XOR it with the key at some point, and we know encryption of this is going to result in just B, right? In the previous case, now B and B will get cancelled out because of the way XOR works. Therefore, we will add. Well, let me correct one thing. Let me correct this so that it's not confusing. Let's call this not C, but let's call this byte as byte X. Okay, you have byte X, you XOR it with B because we know for sure those bytes correspond to B in the plaintext. I'll explain one moment now. And then we XOR it with, what is the next character? 12, right? 12 is the, in hex, it's 0xC, okay? Don't confuse this. This is called the ciphertext. Okay. So what will happen if I modify this particular byte of the ciphertext? Remember, attackers are allowed to modify ciphertext and replace that byte by X XOR B XOR C. When the decryption oracle decrypts it, it's going to XOR this whole thing with the key stream, right? Let's use the letter K for a moment. What will happen now is, or one K stream, people usually call it KS, K stream. The K stream, because of the properties of XOR, we do know when K stream is XOR'd with X is the original position, what do we get? We get B. And now we have XOR'd with, again with B and B will cancel out. So what will happen now is this becomes, instead of B, it will become C. So we are basically making all of the bytes C by moving one position at a time. So thereby, we have changed all the 11 bytes of the resulting plain text to be C when the decryption oracle decrypts. But now padding will fail because this particular position need not be 12, right? Why would arbitrary message be 12? Okay, let's assume it was not 12 for a moment. Okay, in that case, padding oracle will fail. So now how do we go about it? Okay, so here comes another neat trick. So let me first summarize what we achieved so far. What we achieved so far is we found out how many bytes are padded using the simple trick of modifying individual bytes like the previous video had shown, and learned that there are 11 bytes of padding. We tried to change the padding in such a way that when the decryption oracle decrypts, we get 12 bytes of padding instead of 11 bytes. But now the 12th byte from the end is not 12 because it's not a consistent padding necessarily. Therefore, what we are going to do is we are going to start a loop now, starting from 0 to 255. So we will run this simple loop. We will replace this just by 0 and see whether the decryption oracle says it's a problem or not. We try with 1, 2, all the way up to 255. So why are we doing that? Let's assume we modified this byte and replace it by say some byte y. Okay, let's assume we just modified this by some byte y, And suddenly the padding oracle says you're good, you're good. Okay, now what did we learn? We learned that our y, which is be XORed with the key k or k stream, right, resulted in number 12, right? That's the only way padding oracle will say, yeah, your padding is good, which means we learned the key stream now for that particular position. Okay, that's really nice. The key stream is something, the number 12, C in X, XOR with Y. So once you learn the key stream, now it's easy. What is the corresponding message then? The corresponding message, the actual message is just take M. How do you find the actual message? Actual message is extremely simple now. You have your original ciphertext, right? And you just basically XOR it with what? Well, you have the key stream. The key stream is the most important one you need. So you could just take the message, the original ciphertext character at that particular position, which was Y, right? We had Y was a running number that you tried from 0, 1, 255. Let's say this particular position had a value B. Okay, original value was B here at this point. So from a ciphertext perspective, so it's basically B XOR with your key stream KS. Okay, that should tell you what the original message was at this point when we decrypt it. We don't know that, we learned it. What we did is extremely simple. We started a loop, Y being 0, 1, 2, 3, all the way to 255 until we got a padding oracle success. Okay, when we get padding oracle success, we learn the correct corresponding key stream. That now once you know the key stream, you have to take the original byte that was there in the original challenge ciphertext. That's called the ciphertext corresponding character was B. I call it B. B XOR with key stream will give you the message here now. So we learned one character of the plaintext. Now we can do the same. We can now start going here, but then we need to update all of these by 13 instead of 12, which we know how to do it because we already did from 11 to 12. We follow the same algorithm. And then we just again start a loop from 0 to 255 and learn this particular byte. And then this byte and this byte and so on. So it's extremely simple. It's let's say you have a block which is 16 bytes. If 11 bytes are padding bytes, we need to learn the remaining 5 bytes, right? So at most, in average, it's easy. Maybe 128 runs on average for every byte. So it's 5 times 128, which is not much attempts. So that's basically the idea. The idea is that we change the ciphertext in such a way that when the decryption happens, we get into a padding oracle error, and then we start modifying the individual byte until we get a successful padding, and then we know we learned it. Okay, that's basically the idea. So now I'll show you how this works in a simple demo. Okay, just to quickly summarize the main facts is that you have to first step find out how many bytes are padding bytes. That we learned in the previous segment how to find it. Once we find it, we start modifying the ciphertext in such a way that the padding length is increased by 1 in the first iteration, and then we start learning first one more byte of the plaintext. Once we learned that, we start learning the second byte. So we are moving in this direction, right? Learn byte by byte of all the plaintext characters. So I made it simple by just taking only one byte of the ciphertext, just the last byte only I'm decrypting. Okay. All right, let's do the demo quickly now. So let's say I have this padding oracle decrypt demo. I'm initializing it, and the plaintext is of course not known to the attacker. He will get the ciphertext corresponding to A, B, C, D, E, F. Let's see whether he can learn A, B, C, D, E, F. Okay, let's see. Yep, he learned A, B, C, D, E, F. How did he do that? As I have explained to you on the whiteboard. First step is to figure out when A, B, C, D, E, F is encrypted, which he doesn't know whether it was A, B, C, D, E, F or whatever, right? So first step is he gets the challenge ciphertext. He modifies the first byte, he modifies the second byte, third, fourth, fifth, until he get a padding error. Once he get the padding error, he learned the length of the padding, okay, and as well as the length of the plain text. So he learned the length of the plain text is 6, which is true because A, B, C, D, E, F is 6. Therefore, he has to start learning 10 more. So he learned the length of the plain text, which immediately tells us that he also learned all the padding bytes, because all the padding bytes must be 10, 10, 10, 10 times. Okay. So now what he does, he basically knows what is the current state of the plain text, right? He doesn't know all the most significant 6 bytes because that's something he has to learn. He does know the least significant 10 bytes because that's the padding, right? 0A means 10 in hex. So he has 10 times 10, he learned the first iteration. And then what he's going to do, now look at the current ciphertext, okay? It looks pretty much similar to the challenge ciphertext, right? Except one small modification, okay? How many bytes did he modify? He modified the 10 bytes, okay? Let's look at how many bytes look the same. So 1, 2, 3, 4, 5, 6 bytes are the same, okay? All these 6 bytes are the same as here, right? And then you start modifying. What is the modification algorithm? The modification algorithm is very simple. He has to change the ciphertext in such a way that the padding will become, instead of 10 characters, it has to become 11 characters. That's basically what he's going to do. So what he did is exactly what I wrote on the whiteboard. So he changed the ciphertext, so that's the reason why you have a new ciphertext. It was challenge ciphertext. In the first step, he modified the ciphertext, okay? And then he learned, you see here, he learned one more byte. Earlier it was only 10 AAA, that means all the padding bytes. Now he learned 46. 46 in hex means A, B, C, D, E, F. He learned F, okay? And then the next step, he modifies the ciphertext further according to what I explained on the whiteboard, and he learned the next byte of the plain text, which is E. So he does that several times, one by one, and he learned at the end all the bytes of the plain text. As you can see, it's A, B, C, D, E, F. And then all the padding bytes, of course, which he will truncate because he knows the length of the padding. And he got A, B, C, D, E, F, which is pretty neat, that by having this little loop that will modify the ciphertext in such a way that the padding will be wrong, and then he has another loop that runs from 0 to 255 until padding is correct, and then he does a simple XOR manipulation to figure out the individual bytes. So the bottom line is that if there is a padding oracle, the attacker can learn the plain text. So in this demo, I only shown you one block of counter mode. It becomes a little more challenging when you want to consider multiple blocks, but more work will of course lead you to the complete message disclosure. But I think it's good enough to show to you that counter mode, when counter mode is used with padding enabled, you get this problem of padding oracle. I mentioned earlier that Java doesn't really implement padding on the counter mode, but there are other libraries that does implement padding on the counter mode. Those libraries you need to be careful about padding oracle. Okay. One way to prevent this is basically encrypt and then take the ciphertext, do HMAC on the ciphertext, right? It's called authentication, and then send both the HMAC and the ciphertext. So if somebody modifies the ciphertext, HMAC verification will fail. Therefore, they will not be able to learn the plain text like the way we learned today. Okay, that's basically it. Thank you very much.